Hello everybody and welcome to another set of video notes. My name is Mr. Basil and let's get to it. So, this video we're going to be focusing on the topic related to energy of phase changes, and this is closely aligned with Learning Target 6.5 with the College Board. And in this video my objective is that by the end of this you can say I can do energy calculations related to phase change and temperature changes. There are a few things that you need to remember when we're doing this. When temperature changes, you can use Q equals mc delta T to calculate the energy transfer. And a positive or negative sign with Q shows the direction of energy transfer. Now, one thing that you may remember from a previous chemistry class is you can have energy diagrams, and you saw this if you watched the AP Daily video ahead of time. You can see this is going to be called an energy, a phase change, energy transfer diagram. We have temperature. No, not temperature. Energy added down here. Temperature over here. Okay, and we're going to say for water, we're going to call this degrees Celsius. Okay, now let's say that, I don't know, let's start like negative 20 degrees Celsius, somewhere down here. I'm not going to start at 0 because, I don't know, just because. So you've likely seen something like this before. And a big takeaway here is that when there's a phase change, temperature is constant. And we can see that by these flat plateaus that are given in this energy transfer diagram. And the reason why the temperature is constant is because the energy that's going in the system is not making the particles move faster anymore. They're simply overcoming the intermolecular forces, or the forces of attractions between them. Okay, and as such, since the temperature is not changing, we cannot use the Q equals mc delta T equation anymore because there's no change in temperature. So whenever there's a phase change, whether it be melting, boiling, evaporation, or the reverse, freezing, or condensation, the energy transfer has to be using a different equation, which you should already have, but it is this: Q equals M times H. Sometimes you'll see it as delta H, whatever the case is, but it's the molar heat capacity, or the heat fusion is sometimes what it's called, where Okay, so in this case, based off of the way that I've drawn this this diagram, this first one would have to be HF, and this one would have to be Q equals MHV. Okay, and I said that it started at -20, and so then we know that the melting point and freezing point of water would happen at 0 degrees Celsius. And then we'd know that this portion right here, that would happen at 100 degrees Celsius. And this is observably true. And during the temperature change, let's do a different color because it's starting to get a little bit crazy up in this house. So these points of temperature change okay. Then you use Q equals MC delta T, where C is the specific heating capacity or molar heating capacity. And if you're given a molar heating capacity, you're going to want to use the number of moles of the substance to do the calculation. Either way, the idea is the same. And the same thing goes for these M's. Sometimes they could be giving you number of particles, in which case it would be number of moles. And then the heat of fusion would be, like joules per mole instead of joules per gram. Anyway, I'll give you some examples here in a second. And yeah, so if let's say, let's call this, 120 degrees Fahrenheit. No, I'm not going to do this example, but let's say you were given a problem where it said, okay, you're given some solid water or ice at -20 degrees Celsius. How much energy is required for you to bring the temperature of the system all the way up to 120 degrees Fahrenheit? If that was the case, you would have to do 1, 2, 3, 4, 5 separate calculations, because for each of those separate parts, you're going to either use the Q equals MC delta T. So for parts 1, 3, and 5, you'd use that equation. But then the C values would be different, because the C values are going to be different at different phases and different substances. And then for parts 2 and 4, you'd use the Q equals MH equation, where H, the HF is going to be different because the heat of fusion is always going to be smaller than the heat of vaporization. And you'd have to, in the end, add all of those pieces up together in order to get the total amount of energy in the end. And it would be a positive value because energy is going into it. If it was reversed, like how much energy would be required to be taken out of the system to go from 120 down to -20, then it would be the same quantity, but just opposite sign. Now, you may have heard me mention and others mention before that this part of the graph is always going to be bigger or longer on the plateau than this part of the graph. The reasoning for that is because to melt something, you only partially need to overcome intermolecular forces, not completely. So it's always going to be a small little blip there. Whereas the boiling point, you're always going to have a huge amount of energy required to do that, and it's going to be a really flat line there for a long amount of time, because you have to completely overcome intermolecular forces there. So it's always going to be a bigger amount of energy there. And so let's see some data for that right now. All right, here we have our energy transfer diagram. Notice how it's undergoing temperature change right now. It's below the freezing point of water. Notice what the observations are off to the right. All right, now we notice that there's a plateau while it was undergoing melting, and then there's a little bit of strangeness that actually happens there at the end. That jump happens because of it being in contact with the water and the ice. And now here we have just a whole range of temperature change, and then as soon as it starts boiling, it plateaus off, and it will actually continue doing that until all of the water is evaporated out. And there you have it, temperature curve. Now, if you want to you may have noticed a couple things, like the curve kind of like rounded off when it started boiling. If you want an explanation of that, check out the YouTube video that I've linked in the description of this video. That video does a lot of like more detailed explanations. But the main thing you need to take away here is that the reason why there are plateaus when this undergoing phase change is because of the change in intermolecular forces. The particles reach a maximum speed that they can go up at, but then they can't go any faster because that's just because they're bound by the intermolecular forces. Then the energy goes into overcoming the intermolecular forces, and once that's done, then you see the change in temperatures. All right, let's get back to the examples. Okay, so now that we saw like a time lapse of this actually happening, so you can see it, the data actually collected, let's do some calculations and some examples related to this. All right, so here's the first example. It's going to be very straightforward, but how much energy is required to melt 500 grams of water versus boil 500 grams of water? And I have the heat of fusion and heat of vaporization given for both. And you're not expected to memorize these; those will always be given to you. When you're like trying to do a problem like this, sometimes it's easy to, this one's pretty straightforward, but it's never a bad idea to draw your heating curve for this situation. So for this one, it's just, so doink, 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 doink. So we're looking at just doing this part and just doing this part. And so really we just need for each part just one equation. So like just one part. That's it. We don't have to add anything together at all. If we had to do multiple parts of the graph, then yeah, then we have to add them together in the end. But that's not the case. So for melting, we do Q equals the mass, so 500 grams, times so then Q would equal that'd be the melting one. And for boiling, okay, and we can see, we could see just based off the HF and HV values that it's going to take more energy to boil off the water compared to melting it. So there's an example of that. Let's do one that's just a little bit more steps. I want you to try doing that one on your own, and then I'm going to give you an example of a part of a free response question from a previous year. So 2 more examples. All right, so here's your question, and then you can get to it. So how much energy is associated with lowering liquid water from 0 degrees Celsius to negative 15 degrees Celsius? Pause, get to it, and I'll show you the answer here in just a moment. As I'm doing this, I'm realizing you need a couple more variables. So here, I'll give this to you. So HF equals 334 joules per gram, and specific heat capacity of solid water is, I think, I'm just going off the top of my head, but this is the one that we'll use. Sorry if I'm wrong. I believe it's 1.99 joules per gram degree Celsius. lowering liquid water from here, and let's say that the mass of the water is 50 grams. There you go. Now see if you can do the problem. All right, back to it. All right, so here's my answer. I got, it looks like 18,000. I did it quick, so email me if I did it wrong. 18,192.5 joules leaves the system, and so here's how I got that. So once I gave you all the useful information that you needed, I put in 50 grams, put in my heat of fusion, and I got 16,700. But this actually needs to be negative because the math doesn't work out, like there's no adding or subtracting, but that negative tells us that energy is leaving the system, so it's just something you got to be aware of. Not super important, but it does kind of matter when you start comparing it to part 2. Oh, I should explain this. This is a two-parter because we start here, and then it has to freeze, and then it has to cool down a little bit. So this is a kind of a two-parter one where the first part you have to go through a phase change, has to freeze, and then second part it actually has to change its temperature. So 2 parts, 2 calculations. There we go. So that's where my part 2 comes in. You got MC delta T, mass is given to us. I gave you the specific heating capacity of solid water, and then change in temperature, final minus initial. When you put those together, you get this number. And so in the end, I did my Q total equals Q1 plus Q2, and I got this number plus that number, final number here. All right, let's see an example of part of an FRQ from previous years. All right, here you go. This is from 2015. This is part A of a short FRQ, so it's a part A and a part B. But go ahead, pause, see if you can do this, and I'll share with you the answer here in just a moment. Alrighty, ready for the answer? Here we go. So first, in order to set up this problem, you need to recognize that in order to melt the aluminum, it has to start at 298 Kelvin, but it doesn't melt until it gets to 933 Kelvin. And so really what ends up happening here is you need to first heat it up by raising the temperature, and then add energy, enough energy just to melt it. So just to the end of that, so just 2 parts, 1 and 2. And so for part 1, since it's a temperature change, we're going to use Q equals MC delta T, but I put in an N there because it gives us moles. No need to do a conversion here for moles to grams because it actually gives us the molar heating capacity. So molar heat capacity is given. So since it's per mole Kelvin, we don't actually need to do a conversion there because our units are compatible. So for example, when I actually do the unit analysis here, I save that for you guys. So moles cancel out moles. These kelvins cancel out this kelvin, so I'm left with joules. Gives me my answer there. And so that's not so bad. Then use Q equals NHF or MHF, but in this case, again, we're given moles and we're given the molar heat of fusion is given to us, except notice, I made this note here, however, HF is given with kilojoules, so we'll need to watch our units for this one. So this calculation's easy, 1 times 10.7 kilojoules per mole. So I get this, but again, gotta watch it. So do a quick conversion, so 10.7 kilojoules times 1,000 kilojoules cancel out kilojoules. I guess unit analysis, moles cancel out moles up there. Okay, now back to here. That's how we get our total amount of 10,700 joules for part 2. And then we just add them together, part 1 plus part 2, and we get our total answer of that. All right, email me if I made any mistakes or you think I did. I made this video quick, so thanks for listening, everybody, and have a good day.